The things that airplanes are built of have changed a lot since people started putting them together back in 1903. Builders knew they needed something light, so for many years they built the sparsest of wood frames and covered them with cloth. But fabric-covered airplanes were delicate, so some designers went to wood. It was stronger, all right, but it was also heavier and subject to rot. Then they came up with a remarkable breakthrough, a metal so light it could fly. For years, it seemed there would never be anything stronger, until they discovered you could put this together with this, and get this. Composite aircraft construction is far stronger than any method that preceded it, but it achieves its strength only when its two primary elements are bonded together in a process called sandwich construction. These two elements are a fiberglass skin and a foam core. Bill Freeman is a structural engineer for a major corporation. He has done extensive research into composite construction for his own home-built project. Bill gives a demonstration to show the dramatic difference this bonding process makes.
Now, with only the fiberglass, the same 4 plies put together, if we try to show how much load it can carry, we put a brick on it and it sags right down. Now, it doesn't break, but it won't, it's way too flexible. It doesn't have any useful strength. Okay, now the foam core that you use, this is a polyvinyl foam core, same foam core as this piece, exact same size, without any fiberglass. See how much strength the foam core has. You put a brick on it, and it sags immediately. Okay, now we have the sandwich construction. 2 plies of glass on this side, 2 plies of glass on this side, the same foam core. So these are identical in weight. You saw the strength of these. Here, with the sandwich construction, you put the same brick on. It's no problem. Can add another brick, no problem. Can add a 3rd brick, no problem. And we can add a 4th brick. And you can see the relative strength. This is 4 times the load as it took to make these sag all the way to the table, and it's not even near breaking.
Composite aircraft construction, the combination of 2 materials to produce a 3rd, which is substantially altered in structural quality. To learn the technique of composite construction, let's begin with a look at the materials involved. They can be broken down into 3 basic categories: epoxy resins, fiberglass, and foams, or core materials. Now, let's look at each of these categories, beginning with epoxy resins.
The pure epoxy right here, epoxy resin, we'll call it epoxy or resin throughout here. It's somewhat viscous, about like motor oil. It's brown. You mix it up with 2 parts to the proper ratio. Stir it very well together. It's important to stir and scrape the sides. I always make sure I stir at least 2 minutes for every batch of epoxy. It's very important to have it properly mixed, and it's very important to have the proper ratio. If you don't get the ratio right, you won't develop the strength.
By mixing various ratios of filler material with epoxy, you can make other resin mixtures to meet specific needs in composite construction. They are micro slurry, wet micro, dry micro, and flux. The filler for the first 3 of these is micro balloons.
These are micro balloons. This is looks about the consistency of flour. Very, very fine, very, very light material, and each grain is actually a glass bubble.
Micro balloons are simply a means of reducing the weight of an epoxy resin. A 50% mixture of micro balloons to epoxy gives you micro slurry, a liquid which is nearly as runny as epoxy, but only about half the weight. Increase the mixture to 3 or 4 parts microballoons to 1 part epoxy, and you get wet micro. Thicker but still liquid in consistency, ideal for gluing joints. And when you add enough microballoons to achieve a consistency of peanut butter, you have dry micro, a mixture which produces virtually no structural quality, but an excellent lightweight filler for dents and gouges, akin to the body putty used in cars. The final epoxy mixture is flux, so called because instead of using microballoons as its filler, it uses cotton flocking fibers which become very strong when mixed with epoxy. Flux, which is heavier than other fillers, is used when high-strength filler material is required, for developing fillets, as an example. Next, let's look at the fiberglass we'll be working with. As used in aircraft construction, it is fabric composed of strands of glass. There are 2 basic weaves of fiberglass, bidirectional and unidirectional. They are so called because of the direction of their weaves.
The first is bidirectional. If you look at this, you can see that the weave is such that half the fibers run in one direction, the other half run 90 degrees to that. So it has equal strength in 2 directions. It's also woven in what's called a satin weave, where you have 2 fibers over, under 1, then over 2, that allows it to be very drapable, very formable. If you've got a compound curve, you can get BID to drape over it very well, shapes well. On the other hand, it'll level back out if you have to. It'll form into corners well. So this is a very formable material, equal strength in 2 directions, bidirectional. The other material we use is unidirectional cloth. This has approximately 90 to 95% of its fibers running in one direction, parallel. There are cross fibers, but they're very small, and there are just enough of those to hold it together as a cloth so it doesn't fall apart. You want as much of your strength in one direction as you can. It's very, very weak across the fibers, but much stronger than the bidirectional along the fibers. So its strength for its weight is very good if your loads are in the direction of the fibers.
Finally, a look at the various foams which can be used as the core materials in sandwich construction. The principal foams are polyvinyl, urethane, Clark, and polystyrene. Polyvinyl is relatively strong for a foam, and it is not dissolved by fuel. Because of these 2 qualities, it is often used for fuel tanks. Urethane, by contrast, has a very low inherent strength, but it is amazingly easy to shape. Most forming can be done by just a few strokes of a sanding block or even another piece of urethane foam. The strongest of all the foam cores is Clark foam, a thin core material with a high compression strength. Because of Clark foam's strength, it lends itself to be used for hardware attachments, bulkheads, and instrument panels. And finally, polystyrene, also known by a more common name.
This is the styrofoam. Everybody thinks of styrofoam as that stuff in the little white glasses you drink coffee out of that you can crumble in your fingers and it has no strength at all. And when you hear that so-and-so's got styrofoam wings, you kind of go, wow, that's frightening. This is the same material, polystyrene, and it is foamed, but it's a totally different structure. It's a closed cell foam, and it's far stronger than that white foam that everybody thinks of in beer coolers. Plus, its primary use is because you can melt this with an electrically heated wire. It doesn't give off noxious fumes. It melts to a nice clean surface. This surface has been cut with a hot wire, and it's relatively easily shaped with this hot wire technique into airfoil shapes.
Work tip. A number of skin creams are available to protect against the skin irritation often caused by epoxy. We recommend them over rubber gloves, which tend to open the pores so that even a small puncture exposes the skin to irritation. Simply coat the hands and wrists with skin cream to create an almost unnoticeable barrier against the irritation of epoxy resin. Now let's begin learning the technique of composite construction, beginning with a basic flat layup.
This layup would be similar to a layup you'd use in a thin bulkhead or a armrest or a console depending on the design of airplane. But a relatively simple part, not highly stressed, where the layup angles and such aren't quite as important as they would be in a wing or a flying surface.
One of the big advantages of composite construction is the ease of cutting the foam. Once you've laid out the dimensions for a flat layup, cutting the foam with a metal straight edge and hobby knife is almost as simple as drawing a line. A close-up examination of the foam shows it is made up of broken bubbles. Filling those bubbles with pure epoxy would add unnecessary weight. So we'll fill them with micro slurry, which you'll recall adds only half the weight and prevents air from remaining between the glass and foam, improving the bond between them.
So the way we're going to do this is we'll just blob a bunch of this on. One thing that a lot of people, when they first start out with composite construction, worry about is slopping the materials. And what you wind up with then is a lot of wasted time and wasted effort. You got paper towels around to clean up spills and messes, and you want to put the material on in a big bunch. You want to move it around with a squeegee to fill the bubbles. You don't want to spend a lot of time with a brush, daubing it on and working it. All you're doing then is wasting time. You want to just move relatively quickly, get the things covered. You can always squeegee off the excess. There's a lot of worry about weight in parts, and it turns out that spending time dabbing the epoxy on in small amounts is not the way to get good lightweight parts. The way to get good lightweight parts is to work quickly and squeegee well. Now you take your first ply of cloth, and the important thing is to get the fiber orientation in the proper direction. Make sure you're aware of that before you start your layup. For each specific layup, you'll have dimensions given in the plans on the size of glass to use. Here, it's a simple square piece. Notice I've rolled it to try to minimize the distortion, keep the fibers as straight as possible. It's helpful if you do roll it to try to keep them straight. It's always important to try to get your fibers as straight as you can. If the fibers are all over the place, your strength is going to be down. So you want to try to have fibers, in this case, running in a straight line and 90 degrees to each other. And you can get out there and pull on it a little bit like this and wet it out. Now once you get it down, you can rub it out a little bit with your hands, maybe stipple a little with a brush if you want to. Okay, it begins to pick up the epoxy, the slurry from underneath. Now we're going to wet it out. And again, as I said before, you don't want to dawdle around. You dump it out. Everybody wants to use a brush and fiddle with it. That's not the way to do it. You want to pour it out and move epoxy fast. This is the way to make a quick layup. You want to quickly squeegee it out, move it all over the part, get some off the edges. You want to wet out the glass just a little bit beyond the edges intentionally so that later on you can knife trim it. Okay, pretty much quickly wet out the cloth. Again, it helps if you hit it with a little bit of heat. Once you got it pretty much, there'll be some dry areas. Wet those a little bit, or warm those a little bit with the hair dryer. Don't get too carried away. You don't want it to get too hot and cause problems. You could even melt the foam if you got a very hot hair dryer, or soften it. Now the next thing, now I said we're rushing, we're trying to get the epoxy on there. We've got it on there. Now we've got way too much epoxy. Okay? What you've got to do, the next thing is, here's where you make your light layup and save your time. Is you use the squeegee and you start at the center and you very carefully, lightly make a squeegee pass. Right there. See that epoxy that I pulled up? That epoxy should not be in your layup. Epoxy in the layup that's more than the amount to properly wet the fibers is just dead weight. And as weight, it weakens the airplane. It does not strengthen it. So we want to pull that out. So we make a light pass to the edge, we get it into the cup. Another light pass into the cup. Want many light squeegee passes, pulling up epoxy every single time. This is where you put the lightness in your structure, not hours of slowly working the epoxy in with a brush.
Now simply repeat the process to add each additional ply for the buildup called for in the plans. The alignment of each ply will be specified in the plans and is critical for proper distribution of strength. Remember to always align each ply as specified by the designer. After the last ply of fiberglass has been added and thoroughly squeegeed, trim the edges of your layup with a pair of scissors. We recommend you use a pair that you don't mind getting thoroughly coated with epoxy. Make your cuts about a 1/4 inch from the edge. Any more than that can cause your fabric to separate along the edges. Then dab the edges with a brush to bond any portions that may have separated during trimming. And finally, inspect the finished layup for bubbles, wet or dry spots, and distortions in the fiber pattern. These can be worked out with a brush or squeegee. The weave of the fiberglass should be clearly visible but thoroughly impregnated with epoxy. Suppose your plans call for 2 flat layups like the one we've just completed to be joined at a 90-degree angle. Here is how simple joints are made for composite airplanes. To prepare for making a joint, let's go back to the final stage of our flat layup, the point just after we've applied our epoxy to the final ply of fiberglass. Along the edges where the joint is to be made, stipple into the wet epoxy a piece of 2-inch wide Dacron, the kind used on fabric-covered airplanes. In composite construction, these Dacron strips are called peel ply because, as we will see, they will be peeled off later. So leave a little extra on the ends of the strip to help pull it off when the time comes. To ensure a good temporary bond, it will be necessary to add a little epoxy to the outside of the peel ply. This can be applied with a brush. Once you have epoxied the peel ply into position, put the layup aside to cure. When it is cured, you can begin laying up a fiberglass tape. It will be used to bridge the joints.
What we're going to do here is we're going to take our epoxy and we're going to pour some onto some 6 mil polyethylene sheet that we marked out the size that we need to use for these tapes to join these 2 parts together. We put a little epoxy out on there and we roll out an oversized piece of bidirectional. And again, more epoxy, quickly, pat it out a little bit. Okay, as soon as we get that spread at least partially over the part, put our second ply on. Now we got to wet it all the way through. This is going to be used for the brush. We want to brush it pretty good here. We also are going to need to use the hairdryer again. Hairdryer is very important for wetting out these tapes. Okay, now when we get it completely wet out and even, one of the primary advantages to using this plastic technique is now we can squeegee it. This technique of doing it on plastic gives you a very well wet out tape, just the right size, and the plastic stabilizes the tape while you move it. As soon as we've got it properly wet out and squeegeed, we're going to cut out our tape to the size we've already marked on the plastic.
Work tip: always make your tapes to the exact size recommended by the designer. Oversized tapes add no strength, only weight.
There's our tape. Now we have our part that we already laid up, our sample piece. We have our peel ply. Now we're going to remove the peel ply. It's cured already, completely cured. Notice as we pull off the peel ply, the surface behind the peel ply has a matte finish. This is the weave of the cloth showing up. We have peeled off this protective covering and we now have raw, clean epoxy that's never seen the light of day before. It's very easy to pull off and it's very clean. This will make a perfect surface to join to the other part. We'll be joining this like this, a 90-degree joint with a tape in this area. Again, we pull the peel ply. And here we have a perfect surface for bonding. We can join these 2 pieces with some flocks. We take a little flocks, put on excess, and again, wipe off afterwards. We'll want to seat this in place, work it down into position, and wipe the excess. Now we get on and we push a few nails. Now this part's pre-cured, so we're probably going to have to use a hammer to put these nails in. Now we can take the micro we've mixed up previously, dry micro, wipe on a bead of dry micro in the corner, wiped in with your finger to fill what would be an inevitable void there. You'd have an air bubble behind there and it would cause weakness. So we want to fill this with dry micro so that the glass fiber is supported as it goes around this corner. Gives you a good radius. We want to also scrape off all that excess. Okay, we've got the raw surface on both sides ready for attach. We've got micro to fill the corner, and we've got flocks to glue it together. We pick up our plastic covered tape. We lay it in place. Very easy to work with. It's very stable. We work it down into the corner from the middle towards the ends, trying to work out the bubbles. Get it to stick in place. Once we got it pretty well stuck, we'll go ahead and peel the plastic off. Should peel off pretty well. If you pull it along, reversing the direction, you usually don't disrupt the fibers very much, sometimes a little bit, like we have here. Now a little bit of stippling here and there to put it down, and now our tape is in position. It's just much quicker. We have a perfectly wet out tape now in position. The only thing we need now to finish this joint off is peel ply along the edges to make a smooth transition from the 2 plies here onto the full surface. So we're going to put a little extra epoxy along here, just a small amount, and then we're going to put 1-inch wide Dacron peel ply in place and wet it out, strictly to cover this raw edge and give us a nice, smooth, attractive transition between the 2 layups. Turn it around, and we can do the same thing on the other part. This would be typically the last job you'll do on any of your joining operation, joining fuselage halves, putting bulkheads into a fuselage, attaching ribs inside of pre-molded wing type construction. You want to give yourself a nice, smooth transition. A little bit of heat from the hairdryer again helps tremendously on getting these tapes to wet out. There we have the peel ply. Now this part is ready to set aside for cure.
Once the peel ply is cured, remove the peel ply strips. The hardened epoxy underneath should taper smoothly from the 2-ply joint to the sections which have been joined together. Ordinarily, it shouldn't even require sanding. Work tip: to test how your epoxy is curing, save the leftover and let it cure overnight. Then scratch the surface with a nail. This would leave a clean white line if the epoxy has the proper consistency. Of course, not all the surfaces you'll be working with are flat. Let's look now at the technique of airfoil cutting and shaping. Its simplicity is one of the joys of composite construction. It begins with a hot wire saw.
It's a very simple frame. In this case, a 2x4 with some pieces of conduit just stuck loosely into the holes drilled in 2x4. A piece of 41 thousandths or 60 thousandths safety wire, stainless safety wire, stretched between the two and twisted to tighten it up. You got an electrical connection made to each one of these through a transformer and modified dimmer switch that drops the voltage down to about 15 volts through the wire.
Safety tip. Unless you have a thorough understanding of electrical wiring, we recommend you consult a professional electrician for construction of your hot wire saw.
Now we're getting ready to cut our example wing out of this block of foam, which is cut to the right plan form. We're going to use these templates, which are cut from thin plywood, and they represent the airfoil shape at the root of this example wing and the airfoil shape at the tip of the example wing. These will be attached to the foam with nails in the proper positions, and they'll be followed by an electrically heated wire to cut out the airfoil shape from the solid foam core.
First, measure down from the top right corner of the block to the proper position for the trailing edge as specified in the plans. Then position the template by pushing a two-headed nail through a pre-drilled hole in the trailing edge of the template. To ensure exact alignment of the root and tip templates, each is pre-marked with a level line. Pivot the template on the nail till it is perfectly level. Then push a nail into the other end of the template to pin it into position. And finally, push the nails into all the remaining pre-drilled holes, slanting the tip slightly inward to avoid contact with a hot wire during cutting. When all the nails are in place, the properly positioned template will look like this. Now, turn the block around and repeat the process to position the template for the airfoil tip. In this case, you will be measuring from the top left corner of the block so that the trailing edge of the template will be in the same relative position as the other one. Again, tack it into place at the trailing edge and level it. And push the remaining nails into position. Your foam block is now ready for cutting with a hot saw.
Okay, now we're ready to turn on our hot wire saw and check it for temperature. Turn it on, let the wire come up to temp, and we've got just a scrap piece of foam here. We want to push it up against the wire and see. Now that's cutting a little too fast. We want to lower the temperature a little bit. Also getting the wire smoking. Too hot.
A wire that is too hot causes burnback, the melting of the foam along the cut. A wire that is too cold causes wire lag, distorting the airfoil. When the temperature is just right, the wire will slice through the foam almost effortlessly. And the proof that it's correct will be the strands of fibers the wire pulls from the foam when you've completed the cut. To illustrate the hot wire technique for cutting airfoils, let's pretend the foam block is transparent. With an operator at each end of the saw, we'll cut straight down from the top till both ends of the wire are resting on the pins protruding from the leading edge of each template. Then both operators begin cutting along the edges of the templates. To assure that both ends of the saw remain properly aligned, one operator calls out each number he arrives at, and the other adjusts his pace to arrive at each number at the same time.
Okay, ready, straight down, slowly and smoothly into the leading edge, just off of the foil on the pin. We'll wait there a second. I'm on the pin. Okay, moving into one. At point one, moving. And a half, 2 1/2, 3.
If you accidentally lift the wire off the template, no problem. Just go back to the point where you got off track and continue.
8 1/2, 9 1/2, 10 1/2, 11 1/2.
It is essential that the other operator moves from number to number at the correct pace. Failure to stay with the lead operator will distort the shape of the airfoil.
19 1/2, 20 1/2, and we're out of the foam. And we're very good together, and we're pulling good strands of hair off it. Now we'll cut the bottom. We'll go down the same cut, pretty much, and we'll come out and around to the bottom of the pin. Okay, I'm resting on the pin. Okay, we're moving to 1 and moving, and a half, 2, 3 and a half, 4 and a half, 5 and a half, 6, 7, 8, 9.
If your wire hangs up, jiggle it slightly and it should move on easily.
19. Okay, we want to pause at 20, hold it, moving. 21, 22, out.
Now remove the weights from the block, take out the airfoil, and examine it. That raised portion along the trailing edge will be used later in constructing the trailing edge joint for the skin. Along the leading edge, the flashing will remain from the pins where you started your cuts. Simply break it off with your fingers. Then remove the templates from both ends. Then sand the leading edge where you've broken off the flashing, taking care to preserve the original airfoil contour. While other airplane wings get their primary strength from a wood or metal spar, the spar of the composite wing is a fiberglass layup. It is a C-shaped layup of a shear web and 2 spar caps running from the root to the tip. To make the spar, we first want to cut off the leading edge of our airfoil at the spar location noted in the plans. We have supported the airfoil in the foam it was cut from and pinned a template vertically to guide our cut. Our airfoil is now divided into 2 components, the leading edge portion and the trailing edge portion. The leading edge may be laid aside for now, while the front corners of the trailing edge portion are rounded to make a radius for application of the shear web. Once the shaping is completed, jig the trailing edge portion into a vertical position and mask off the portion behind the spar location. Now apply a layer of micro slurry to the portion of the airfoil to be covered by the C-spar. The application is the same as we demonstrated in the flat layup.
Okay, that looks just great. All right, now we're ready to roll out the first ply of glass. This is bidirectional. Got it on here so that the fibers are running at 45 degrees to the surface. The fibers are running this way and this way.
Again, the process of applying the glass is essentially the same. After our first ply of glass is in place, we'll wet it out thoroughly by brushing on a coat of pure epoxy.
Okay, now the second ply of cloth gets laid on.
Notice that the second ply of the cloth is a little more than half the length of the first ply. This is another advantage of composite construction. Because the root of the airfoil will be subjected to higher stresses than the tip, we can beef it up with an extra ply while saving that weight on the tip where it isn't necessary. Once we've positioned the second ply, we'll trim the edges on both sides of the airfoil. In this case, it's best to trim them just a bit short in order to prevent a ridge in the airfoil. After we have wet out and squeegeed the final ply, we are ready to join the leading edge back into place on the airfoil.
Got dry micro, little bit wetter than normal. I'm going to build a ridge of this up in the center so it'll squeeze outward with no air bubbles in it, or a minimum number of air bubbles in it, to make a good joint to bond the foam leading edge back in the same position it was in when we hot wired it.
As you seat the leading edge, push it gently back and forth to work out the air spaces in the wet micro. Be careful to line it up exactly as it was originally, then push nails through the seam to hold it firmly in position while the dry micro sets up.
Nail holes, those are easily fixed later on. We'll show you how to do that.
With a piece of peel ply covering the spar layup, use a few dabs of 5-minute epoxy to glue the airfoil back into the block it was cut from, and to glue the block to a piece of plywood or your workbench top. After the spar has cured, we will be ready for the step that gives the spar the majority of its strength, the layup of the spar cap on both sides of the airfoil. This is done here with a process called flagging. After removing the peel ply from the spar, brush on another coat of epoxy.
Okay, now we've cut our unidirectional glass. in such a way that it will, as we fold it over, it will taper, and we'll get a tapered spar cap here. This spar cap is going to be the main structural part of the wing spar in this wing. So it's important that the fibers run very straight down. So we want to pull these with our hand and get them nice and smooth.
The purpose of flagging is to economize on weight by building a spar cap that increases in thickness from tip to root. As we make our layup, we will continually fold the unidirectional back up on itself until we have constructed a cap that is 1 ply thick at the tip and multiple plies thick at the root. Thoroughly wet out the first ply. Then carefully fold it over.
And you want to fold it right back on itself and lay it right down, keeping the fibers straight.
Now slit the fibers along the fold with a razor blade to make the cloth lie flat. Then wet out the second layer, brushing on another coat of epoxy. And fold the unidirectional back upon itself again to make the next ply. Continue the process till the last layer is in place.
All right, we have 1 ply, 2 plies, 3 plies, 4 plies. So the inboard end of this example wing has 4 plies of unidirectional cloth in its lower spar cap, and it tapers to only 1 ply at the tip.
Finally, trim the excess fabric from the spar cap and squeegee off the excess epoxy. This flagging process is used in building up small spar caps, but in larger airfoils, such as wings, a thicker grade of glass in the form of a unidirectional tape is used to achieve the greater thickness required with less time and effort. We are now ready to transform our airfoil into fiberglass with the layup of the skin. You will note that the basic procedure is the same used in flat layup.
So let's lay the slurry up on here and squeegee off the excess.
Using pieces of two-sided cellophane tape as a temporary adhesive, we'll stick a piece of peel ply to the raised trailing edge of the airfoil.
Carefully lay it in position.
This will be removed later to join the top and bottom trailing edges. Then use dry micro to fill any nicks or nail holes and the groove remaining where the spar has been rejoined to the leading edge. Be careful to keep the dry micro off the spar cap to ensure good bonding between the spar cap and the skin.
Okay, now we've got the surface prepped, all the nail holes filled in the gap. We're ready to put the first skin on it. This first layer of skin on this particular wing is going to be oriented from this point to this point. The fibers are going to be oriented this way, all the way along. It's unidirectional cloth, first ply of skin.
It is best not to pre-cut the cloth. Lay an ample portion of it over the airfoil and align the fibers. Then cut the cloth, leaving a large excess on each side of the airfoil, and fine-tune your fiber alignment.
Okay, that's pretty good.
To achieve maximum strength, your fibers must run in a straight line, in this case diagonally, from root to tip. Once the fabric is in place, it's time for a familiar procedure, wetting out the cloth with epoxy. And remember, don't skimp. The excess will be squeegeed off after the final ply is wet out.
Okay, that's ready. Ready to put on the next ply. Okay, just let it unroll. Now this ply is going to be oriented from this corner to this corner across.
Once the fabric is in place, repeat the wetting out process on the second ply. When the layup has been pretty well squeegeed out, trim the fabric around the edges to within about a ½ inch of the foam.
Now, the trailing edge, you want to carefully stipple that down into the groove and against the previous plies. You need to add a little more epoxy here. Don't want to be too wet because it's pretty hard to squeegee down an area like that, but we do want to make sure we get it wet out all the way.
Remember, a hairdryer can be used to speed up any wet out. Then give the airfoil a final squeegee, pulling in the direction of the fibers to prevent distorting them. Then leave your airfoil for curing.
Speeds up the wet out of the fibers.
When it's cured to the knife trim stage, do a final knife trim of the fiberglass all the way around. If you let the cure run too far, a hairdryer will quickly soften the fiberglass for easy cutting.
And now that we have it knife trimmed all the way around, we're ready to peel it off of the female piece of foam that we cut it out of, turn it over and jig it the other side to lay up the other side. So we'll just pop it off.
Now make the female jig for the other side of the airfoil and cut a few inches off the leading edge. This will give us clearance to make our leading edge overlap of the top and bottom skins when that time comes.
Okay, now that your 5-minute epoxy is cured and the part is securely fastened to the bench, we're ready to prepare the trailing edge. Remove this tooling block of the foam and get ready to make the proper lap joint in the trailing edge. You take your knife and you just start hacking off the foam. So keep cutting and pulling it off as you go. You're just doing a rough cut here. Remove the majority of the material in a hurry with the knife. There's no need to be very precise with this. Okay, now you've got all that trimmed. Take your long sanding block and you want to carefully smooth this up until it's just about matched in now. Okay, at this point, we're ready to lift the peel ply that we put on with a sticky tape in the previous layup. This will be a little difficult to get started. You may need an X-Acto knife. Okay, once you get it started, you can peel it off, and as you peel, you've got a new fresh surface underneath, which will be perfect for bonding the top skin to. So you get a strong trailing edge closeout. This trailing edge closeout is a critical part of the airfoil. To prepare the leading edge for a lap, we'll turn around so you can see it better. We'll want to do a light bit of sanding on here, rolling it around so that as the leading edge skin comes over and laps on the bottom, we'll have a sanded surface for it to lap onto, and we will have no abrupt transition. We want this smoothed down. So it'll just take a little bit of sanding. You want to sand on the glass, not on the foam.
The layup of the spar cap and skin on the second side are done just as on the first side. As the skin is cured, the trailing edge peel ply is removed and the trailing edges are bonded together. Once the final layup has cured, we'll need to turn the airfoil over and fill the trough that was made when we epoxied the top and bottom trailing edge skins together for a strong trailing edge closeout.
We fill that with dry micro. It's very easy to fill with micro and strike it off smooth. It'll require a little bit of sanding later on, but it's relatively quick and easy to do this. Now that we've got it pretty well filled, we have a little bit of excess in a few spots. It can be easily sanded off later, and we'll trim the trailing edge when it's gotten fully cured and hard. We don't want the possibility of hitting a trailing edge and separating this. We'll also need to sand the leading edge a little bit to smooth it up, clean up some of the 5-minute epoxy that held it down for the layup on the other side, and we'll need to go through the finishing process to fill any irregularities and to give the final smooth surface that you see on a composite structure. But this structurally is essentially complete.
I'm sure you'll agree that the composite method is not just a revolution in aircraft construction. It's a revolutionary skill with little similarity to any which preceded it. So it's going to take a lot of practice to master this new art form. We suggest you watch this tape several times and do some trial layups of your own before setting about to build your own airplane. And we recommend that you supplement your knowledge of composite construction by reading about it. Here is a suggested reading list. Introduction to Composite Technology by Luce. Composite Construction for Home-Built Aircraft by Lambie. Plastics Materials and Processes by Schwartz and Goodman, Composite Aircraft Design by Holman, and Handbook of Composites by Lubin.